Our final family of reactions that we're going to look at in this unit are the ones that many of you are familiar with already, the ones that go boom, the ones that are called combustion reactions. So combustion reactions are actually quite easy to identify because 3 out of the 4 reaction products never change. One of the reactants and 2 of the products are always predictable. The fuel is the only thing that changes. So the 2 reactants that are featured in combustion reactions are called a hydrocarbon fuel. A hydrocarbon fuel is just a fancy word for a molecule that has hydrogen carbon in it, but for our purposes in studying combustion reactions, we're going to add some oxygen possibly in there too. The only thing that makes one fuel different from another is the ratio of carbons and hydrogens within that fuel. We have everything from methane, which is 1 carbon and 4 oxygen, 1 carbon and 4 hydrogens together, versus something like gasoline, which is called octane, which is C8H18. And there's many, many possibilities from there. So the one reactant is a hydrocarbon fuel, and the only way we can get things to burn is if they are in the presence of oxygen. And the oxygen is always found in our air. 21% of the air that we breathe consists of diatomic oxygen. So the products of combustion when we do burn these hydrocarbon fuels are always, always, always carbon dioxide and water. And if this is the case, of course, we call this complete combustion. However, there is a scenario whereby the reaction combustion products are not carbon dioxide and water. We want to take a moment to talk about that scenario. So if hydrocarbon fuels like propane, gasoline, methane, ethanol, acetylene, any of those are burned in closed spaces like garages or shops or houses or tents or something along those lines, then what happens is as the combustion goes on, the amount of available oxygen starts to decrease as it gets used up, and there isn't a fresh supply as when you burn it outside. And when that happens, other undesirable products can be created in that combustion reaction. Those undesirable products consist of, carbon or soot. Think about the campfire residue that you have at the bottom of the pit, where the amount of oxygen is limited by the container that's holding that fire pit. And you can also get the one that's really of concern to us, which is called carbon monoxide. Carbon monoxide is incredibly toxic to humans in that we don't know we've exposed to it often because it's colorless, it's odorless, it's tasteless. And by the time you are inhaling carbon monoxide, you get really sleepy, really disoriented, and you may not have the common sense to get out into an open space. And so when that happens, this is called incomplete combustion. This is one of the reasons too that's incredibly important if you have any sort of gas appliances, or if your home is fueled by gas or even by wood as well, that you have to have a carbon monoxide detector on every level of the house for the safety of its occupants because, as I said, can't taste it, can't smell it, and so on. All right, so from a chemical standpoint here on paper, let's look at what combustion reactions look like from words, chemical equations, and structural equations too. I'm going to choose to use ethanol as our first hydrocarbon fuel. It's one that is found in alcoholic beverages. It's one that's found in flambés if you're into sort of fancy foods. And it's also found now as a fuel for cars and trucks. So when it reacts with oxygen, it produces carbon dioxide and water. And what we'll do is we'll always assume complete combustion unless I tell you otherwise. So if we put that into words, and I don't expect you to know what the formula of ethanol is, so I would have to give that to you. Ethanol's formula is C2H5OH, and oxygen, of course, as an element is O2. Carbon dioxide and water are relatively straightforward. What I've done here is I've actually taken a moment to sort of draw what they would look like if we built them with the model kits, because of course in combustion here we're dealing with all non-metals, carbon, oxygen, and hydrogen, and I've actually used their respective colors more or less in the structural equation too, other than carbon is black in our model kits, and here I've shown it as gray. What I'm going to do is I'm going to use the structural equation to help us balance it. One of the great acronyms that you can remember to balance any type, and I mean any type of combustion reaction, is a little acronym I call CHO. And CHO means balance carbon first, then hydrogen, and then leave oxygen to the end. And let's show you how this works. If we look at the left side of the equation, we see 2 carbon atoms, and on the right side we only see 1. So we're going to bring out our cloning tool here to get us to the point now where there are 2 carbons. And so in our acronym CHO, carbon is now balanced. If we look at hydrogens, we see on the left-hand side there are 6 altogether, but on the right-hand side there are only 2. So again, we can bring out our cloning tool and we can create a total of 6 hydrogen atoms via 3 water molecules. So the last thing that we need to balance now, according to Cho, is oxygen. And one of the great things about leaving oxygen to the end is we have O2 as our reactant product on the left. And because it's an element, we can essentially put any number we want in front of there, and it won't disrupt any of the other elements that we're balancing in that chemical equation. So we see on the right-hand side that we have a total of 4 oxygens from this particular contributor and 3 from here for a grand total of 7, which means that on the other side, we also need 7. Let's take a look at our inventory. Here we have 1 already, and here we have 3. And I've already told you, let's focus on what can we multiply this one by in order to get what we need on the other side. Because there's 1 already present, we actually don't need 7 anymore. We actually need 6 that come from this O2 term. So what can we do the O2? Well, we can clone it. And when we, well, let's try that again. There we go. And when we clone it, we can see now that there's 1 oxygen from here, and there are 6 from here to give us our grand total of 7 on the left. So let's summarize up in the chemical equation how many of each reaction species it took to balance the equation. It took 1 ethanol, it took 3 oxygens, it took 2 CO2s, and it took 3 waters. And then we're done. Let's take a look at one more combustion reaction. Let's look at a fuel called acetylene, which is welder's gas. Acetylene burns at incredibly high temperatures, and therefore it's great for melting metals. So if it reacts with oxygen, it can produce carbon dioxide and water. And so the chemical equation for, or the chemical formula, I'm sorry, for acetylene is C2H2. And the other 3 reaction species, as I mentioned earlier in the video, oxygen, CO2, and water, are always staples or things that are constant to help identify a reaction as a combustion reaction. Now, if we look at it from a molecular model standpoint, we can see that they would look like this. And the acetylene actually has a triple bond between the carbons, and we're going to start by balancing carbon. Because, remember, we have this acronym CHO to remember when balancing. So if I do the carbons first, I notice that there are 2 on the left, but there's only 1 on the right. So let's take a moment then and balance carbon. We can see on the left-hand side there are 2 hydrogens, but lo and behold, on the right there are also 2 from that water, and therefore hydrogen's already balanced. So that leaves us now with oxygen to balance as our final one. So let's take a look. On the right-hand side, I have 4 from this set of reactants, or products, sorry, and 1 from here for a grand total of 5 oxygens. Now, this becomes a problem for us when we're balancing by CHO because the number of oxygens we need is odd. And we're dealing with a hydrocarbon that has no oxygens in it. So all of the oxygens have to come from O2. But no matter how I clone O2, I'm never going to be able to get 5. I can get 5 if I do 2.5. And 2.5 oxygens is the same as having, 2 halves and another 2 halves, and a half, which is the same as 5 halves. But ironically enough, in the chemical world, we are allowed to put fractional coefficients in front of diatomic molecules only, oxygen being one of those. So I can actually stop at this point and put 5 halves. And if you look at that and go, I'm never going to remember that, do remember this. When you end up with an odd number, you can go up to your oxygen and you can put something over 2. And then the question becomes, well, what is that something? Well, that something is this number right here, the 5. And all I have to do then is put the 5 on top. And I'm done balancing the equation. I don't have to go back and fix anything. So that's one way to balance a combustion reaction when the number of oxygens you end up with on the right side is odd. There is another solution though too, and I'm going to show it to you in green. What we can do instead is we can go back and we can double some things. If we go back specifically and begin by doubling the fuel, what that's going to do for us is beforehand we had 2 of these and 1 of these. And we had, so let me go back here, we had 1 of the fuels. Okay, so if I go back and if I double that fuel, so this is option number 2 for balancing this equation, I can get 2 of those. What that's going to force me to do is to double the carbon dioxides and of course double the waters because the carbons and hydrogens have doubled on both sides. If I take a look now using the green notation, how many oxygens do I have altogether? Well, if I have 4 CO2s, I'd have a total of 8 from this species, and I'd have 2 from this species, which is a grand total of 10. So how many O2s would it take in order to have 10? Well, it would take 5. Okay, because 5 times 2 would be 10. And so the green method is another way you can balance that's perfectly acceptable and avoids fractional coefficients. But if you run into doing CHO and you get an odd number, you can just simply stop there, use the 5 halves for this particular example, and be done as well. Both methods are perfectly acceptable. So again, long story short, combustion reactions, easy to identify because you have some sort of hydrocarbon fuel that might have oxygen in it as well. You always, always, always have oxygen reacting with that fuel. And in the case of complete combustion, you always, always have CO2 and you always, always have water. If it's incomplete combustion, you also might have, with that carbon dioxide and water, some solid carbon and some carbon monoxide, and the ratio of those could be all over the place. Moral of the story, always perform combustion reactions where there's a great deal of oxygen present, in other words, in the outdoors.